Welcome! In this session, we'll explore problem number 318, maximum product of word lengths. This is an engaging problem that combines string manipulation with optimization techniques. We'll break it down step by step and discuss efficient approaches. Let's dive in. The problem asks us to find the maximum product of the lengths of two words from a given array of strings, where the two words do not share any common letters. For example, in the array abq, baz, foo, bar, xtfn, abcdf, we need to identify two words that are disjoint, meaning they have no overlapping letters, and then compute the product of their lengths. If no such pair of words exists, the output should be 0. The input is a list of strings, where each string contains only lowercase English letters. The output is an integer representing the maximum product of the lengths of two disjoint words. Let's examine a few examples to clarify this further. In the first example, the input array is abq, baz, foo, bar, xtfn, abcdf. The output is 16. This is because the two words abq and xtfn do not share any common letters. The length of abq is 4, and the length of xtfn is also 4, so their product is 4*4 equals 16. This is the largest possible product of lengths for any two disjoint words in this array. In another example, given the array of abc, d, cd, bcd, abcd, the output is 4. Here, the words ab and cd do not have any overlapping letters, and their lengths are 2 and 2 respectively, giving a product of 2*2 equals 4. Let's see one more example to cover edge cases. Consider the input, AA, AAA, AAA. In this case, the output is 0. This is because every word in the list contains the letter A, meaning no two words are disjoint. As a result, there are no valid pairs of words to compute a product, so the result is 0. Now that we've seen how the output is calculated for various scenarios, let's review the constraints and edge cases to better understand the problem's scope and requirements. The constraints specify that the input list words can contain between 2 and 1,000 words, and each word can have a length between 1 and 10,000 characters. Additionally, every word is guaranteed to consist only of lowercase English letters, and all words in the input list are unique. Some important edge cases to consider include when the input has the minimum size of 2 words, where we must verify if they share any common letters. Another case is when all words in the list share at least one letter, resulting in an output of 0. We also need to handle varying word lengths effectively and ensure that the solution performs efficiently when dealing with the maximum constraints, such as 1,000 words with each being up to 10,000 characters long. Addressing these scenarios is crucial for a robust solution. To solve this problem, let's begin with the brute force approach. The intuition here is straightforward. For every possible pair of words, we check if they share any common letters. If they don't, we calculate the product of their lengths and keep track of the maximum product we find. The implementation involves iterating through all pairs of words and comparing their characters one by one to check for common letters. If no common characters exist, we calculate the product and update our maximum product if necessary. While this approach is simple and doesn't require extra memory, it has significant drawbacks. The time complexity is n squared times m, where n is the number of words and m is the average length of a word, as we repeatedly iterate through characters to check for overlaps. This makes it inefficient for large inputs. Furthermore, since we don't store any intermediate results, we end up performing redundant checks, which further increases the computational cost. These limitations highlight the need for a more optimized solution. To address the inefficiencies of the brute force approach, we can use an optimized approach based on bit manipulation. The key idea here is to represent each word as a 26-bit bitmask, where each bit corresponds to a letter from A to Z. If a word contains a specific letter, the corresponding bit in the mask is set to 1. This allows us to quickly check if two words share any common letters using a bitwise AND operation. If the result of this operation is 0, it means the two words have no common letters. Implementing this involves first pre-computing the bitmask for each word based on its letters. We also store the length of each word alongside its mask. Then, we iterate through all pairs of words, checking their bitwise and if it's 0, we compute the product of their lengths and update the maximum product. The key observation here is that using bitmasks reduces the cost of checking common letters from O, M, to O, 1 per pair. Additionally, pre-computing the bit masks avoids redundant comparisons. This approach has a time complexity of O, n squared plus n times m, where n is the number of words and m is the average word length. The space complexity is O, n, as we need to store the bit masks for each word. While this is a significant improvement, we can further optimize by sorting the words by length in descending order and stopping comparisons early if the maximum possible product becomes smaller than our current maximum. However, this adds implementation complexity and is useful only in specific cases. Among the approaches considered, we chose the optimized approach using bit manipulation as our primary strategy. This method is efficient because it reduces the cost of checking for common letters to 0.1 per pair, thanks to the bit mask representation. While the brute force approach is easier to understand and implement, it becomes computationally expensive as the input size grows. The bit manipulation approach, on the other hand, offers a much better balance between efficiency and clarity. As for the sorting-based optimization, while it can reduce the number of comparisons in some cases, it introduces additional complexity and doesn't always provide significant benefits unless the input size is extremely large. In terms of trade-offs, the brute force method is simple but inefficient. The bit manipulation approach requires a pre-processing step to compute the bit masks but is highly efficient during pairwise comparisons, and the sorting optimization adds complexity without a guaranteed improvement in all scenarios. Ultimately, the bit manipulation approach stands out as the most efficient and practical solution for this problem, striking the right balance between performance and simplicity. To solve the problem, we are given a list of words, and our task is to find the maximum product of the lengths of two words that do not share any common letters. The first step is to parse the input, which is simply a list of words like ABC, def, gh, add. The goal is to identify pairs of words that meet the condition of having no shared letters and compute the highest product of their lengths. To streamline this process, we represent each word as a bit mask. Each letter of the alphabet corresponds to a unique bit in a 26-bit integer. For example, A corresponds to bit 0, B to bit 1, and so on up to Z, which corresponds to bit 25. For a word like ABC, the bits for it should be, and C are set to 1, resulting in a bit mask of 7 in decimal, or 000000111 in binary. This representation allows us to efficiently check for common letters using bitwise operations. Once we compute the bit mask for each word, we store these bit masks along with their corresponding word lengths in a data structure such as a dictionary or an array for quick access. The next step involves comparing these bit masks to identify pairs of words that do not share any common letters. For each pair of words, we use the bitwise and operator to check if their bit masks overlap. If the result of bitmask_i and bitmask_j equals 0, it means the two words have no shared letters. When we find such a pair, we calculate the product of their lengths and update the maximum product if the new value is larger. After examining all possible pairs, the algorithm returns the highest product found, which represents the answer to the problem. The use of bit masks brings several key advantages to this algorithm. First, it significantly reduces the complexity of checking for shared letters. Instead of comparing each character of two words, which could take time proportional to their lengths, a single bitwise operation suffices, making this step constant time. Second, pre-computing the bit masks for all words ensures we only perform this calculation once per word, avoiding redundant work during the comparison phase. Finally, we can optimize further by considering the lengths of the words. If the product of two word lengths is guaranteed to be smaller than the current maximum product, there is no need to compare their bit masks, saving additional computation time. These optimizations make the algorithm both efficient and scalable for larger inputs. To implement this efficiently, we use an array or similar data structure to store each word's bit mask and length together. This allows for quick access during comparisons. The core of the algorithm relies on bitwise operations, such as and to check for shared letters and or to manipulate bit masks if needed. In terms of complexity, pre-computing all bit masks takes O, n asterisk L, where n is the number of words and L is the average word length. Comparing all pairs involves O, n squared, comparisons, leading to an overall complexity of O, n times L plus n squared. It's also important to handle edge cases gracefully. For example, if the input list is empty or has only one word, we simply return 0 since no valid pairs exist. Similarly, for very large words that use all 26 letters, the bitmask calculations must correctly account for all bits without errors. Lastly, when words share letters, they are automatically skipped during comparison, ensuring correctness. Let's walk through a concrete example using the input words ABC, def, gh, add. In the first step, we compute the bitmask in length for each word. For ABC, the bitmask is 7, and the length is 3. For def, the bitmask is 56, and the length is also 3. For gh, the bitmask is 192, with a length of 2. Finally, for add, the bitmask is 9, and the length is 2. Next, we compare all pairs. For ABC and def, the bitwise in of their bitmasks is 0, meaning no common letters, so we calculate the product as 3 times 3 is equal to 9. For ABC and GH, the in is also 0, but the product is 6, which doesn't exceed the current maximum. When comparing ABC and add, the in is non-zero, so they share letters and are skipped. For def and GH, the in is 0, with a product of 6. After evaluating all pairs, the maximum product is 9, which is returned as the result. This implementation solves LeetCode problem number 318, maximum product of word lengths using bit manipulation. Here's a detailed explanation of the code. 1. Input parsing and initialization. We start by creating two arrays, bitmasks and lengths. The bitmasks array will store a unique integer representation for each word, and lengths stores the length of each word. 2. Bitmask representation. Each word is converted into a bitmask that uses a 26-bit integer, 1 bit for each letter A to Z. For example, the word ABC will have a bitmask where the first 3 bits are set, binary, 111. This is done by iterating over the characters in the word and setting the corresponding bit using a bitwise OR operation. 3. Finding the maximum product. To find the maximum product of lengths of two words with no common letters, we iterate through all pairs of words, I, J. If the bitwise in of their bitmasks is 0, bitmasks, I, and bitmasks, J, equals 0, it means the words have no overlapping letters. In this case, we calculate the product of their lengths and update max_product if the product is greater than the current maximum. For edge cases, the algorithm handles edge cases such as an empty list of words returns 0. Words with repeated letters, these are correctly represented in the bitmask. 5. Efficiency. By using bitmasks, we efficiently check for common letters between two words in constant time, reducing the overhead compared to character-by-character comparison. The overall complexity is n squared, for the pairwise comparisons, where n is the number of words. In summary, this solution leverages bit manipulation to efficiently solve the problem while maintaining clarity and correctness. Here we start by defining a class solution and implementing the method maxProduct, which takes an array of strings called words. The goal here is to determine the maximum product of the lengths of two words that do not share any common letters. First, we initialize the necessary variables. The array bitmasks will store a bitwise representation of each word, where each bit corresponds to a letter in the alphabet. The lengths array will store the lengths of each word for quick access later. In the first loop, we iterate through all the words, and for each word, we calculate its bitmask. This is done by setting a bit corresponding to each character in the word. For example, if a word contains the letter A, the first bit is set, if it contains B, the second bit is set, and so on. This allows us to efficiently compare words later to see if they share any common letters. At the same time, we store the length of each word in the lengths array for later use. Once the bitmask and lengths are computed, we proceed to the next step where we calculate the maximum product of word lengths. Now, the function continues by iterating through all pairs of words using a nested loop. For each pair of words, we check if their bitmasks have no overlapping bits using a bitwise AND operation. If the result is 0, it means the two words do not share any common letters. When this condition is satisfied, we calculate the product of their lengths and update maxProduct if this product is greater than the current maximum. After all pairs have been checked, the method simply returns the value of maxProduct, which represents the maximum product of lengths of two words that do not share any letters. This approach ensures an efficient comparison using bitwise operations while maintaining clarity and simplicity in the implementation. To solve this problem, we start by representing each word as a bitmask. A bit mask is a compact way to represent the unique letters in a word using bits. For the given input, we initialize two arrays, bitmasks to store the bitmask for each word and lengths to store their respective lengths. For example, the word apple has the letters of B, C, and W. Each letter corresponds to a specific bit position, so we calculate the bitmask by setting these bits. For apple, A sets the first bit, B the second, C the third, and W the 23rd. Combining these gives a bitmask of 4194311. We repeat this for all words, resulting in the final bitmasks array 4194311, 33554435, 133, 163, 16416, 63. This step efficiently encodes each word's unique character set for quick comparisons in the next step. Now that we have the bitmasks, we proceed to compute the maximum product of the lengths of two words that share no common letters. To do this, we initialize max_product to 0 and compare all pairs of words using their bitmasks. If the bitwise in of their bitmasks is 0, it means the words have no overlapping letters, and we calculate their product. For example, abq and baz have no common letters, so their product is 4 times 3, which equals 12. We update max_product to 12. However, abq and foo share common letters, so we skip their product. After evaluating all pairs, the largest product is found between abq and xtfn, both of length 4, with a product of 16. Thus, the final result is 16. In this second example, we follow the same process. First, we convert each word into its bitmask representation. Starting with a, which has only one unique letter, its bitmask is simply 1. For ab, the letters at end set the first and second bits, resulting in a bitmask of 3. Similarly, ABC has the letters of B and C, giving a bitmask of 7. The word D sets the fourth bit, resulting in a bitmask of 8. Continuing this for all words, we find the final bitmasks array 1, 3, 7, 8, 12, 14, 15. These bitmasks allow us to quickly identify which words share common letters in the next step. With the bitmasks ready, we now compute the maximum product. Starting with the pair at and D, their bitwise in is 0, meaning no common letters. The product of their lengths is 1 times 1, which equals 1, so we update max_product to 1. Next, for ab and CD, their bitwise in is also 0, and their product is 2 times 2, which equals 4. We update max_product to 4. For ABC and D, there are no common letters, but their product, 3 times 1, is smaller than the current maximum, so no update is made. After evaluating all pairs, the largest product is 4 ab and CD, with a product of 4. Thus, the final result is 4. In this final example, we have words that all consist of the letter A, repeated multiple times. When we calculate the bitmasks, each word's bitmask is simply 1, because there is only one unique letter. With all bitmasks being identical, any pair of words will have a bitwise and that is not 0, meaning every pair has common letters. As a result, no pair satisfies the condition of having no overlapping letters, so no products are calculated. The maximum product remains 0, and the final output is 0. To analyze the time complexity, the solution can be broken into two main steps: constructing bitmasks for each word and performing pairwise comparisons of those bitmasks. In the first step, we iterate through each word in the list, which has a total of n words. For each word, we compute a bitmask by iterating through its characters. If we let k_i be the length of the ith word, the total time for this step is proportional to the sum of the lengths of all words in the list. This total length is denoted as s, making the time complexity of this step O(s). Moving on to the second step, we compare every pair of words to check if they share any common characters. Since there are n words, the number of pairs is given by the combination formula n*(n1/2), which simplifies to O(n²). Each pairwise comparison involves a bitwise in operation, which is O(1), because the bitmask size is fixed at 26 bits. Therefore, the time complexity of this step is O(n²). Now, combining the two steps, the total time complexity is O(s plus n²). In the worst case, the total length of all words, s, can be as large as n*(m), where m is the maximum length of any word. This means the overall time complexity becomes O(n times m plus n²). Depending on the input, if n squared dominates n asterisk m, the complexity simplifies to O, n squared. Otherwise, it remains O, n times m plus n squared. For space complexity, we first consider the bit masks. We store one bit mask per word, and since each bit mask is a fixed 26 bits, the space required for bit masks is proportional to the number of words, or O, n. Additionally, we store the lengths of all words in a separate list, which also requires O, n, space. Finally, any temporary variables used in loops or operations take constant space, or O, 1. The total space complexity is therefore O, n, with the storage of bit masks and word lengths dominating the space usage. To understand why this approach is efficient, let's compare it with the brute force method. A naive solution would check every pair of words and explicitly compare their characters to determine if they share any common characters. This would involve O, n squared, pairs, and for each pair, comparing all characters of two words, which in the worst case takes O, m squared, for words of maximum length m. This gives the brute force method a time complexity of O, n squared asterisk m squared. In contrast, the optimized approach using bit masks reduces the cost of comparing two words to O, 1, resulting in a time complexity of O, s plus n squared, or O, n times m plus n squared, in the worst case. This represents a significant improvement, especially for large inputs. Analyzing further, in the best case scenario, if the input list is empty or contains only one word, no comparisons are needed, and the complexity is O, 1. For the average case, with a random distribution of words and lengths, the complexity is O, s plus n squared. In the worst case, when all words are of maximum length m and there are n words, the complexity becomes O, n times m plus n squared. To mathematically confirm the big O, the bit mask construction depends on the total number of characters across all words, which we represent as s equals sum, len, word, for word in words. This contributes O, s, to the complexity. Pairwise comparisons contribute O, n squared, due to the quadratic number of pairs, with each comparison taking constant time due to the fixed bit mask size of 26 bits. Combining these, the total time complexity is O, s plus n squared. Depending on which term grows faster, s or n squared, the worst case complexity simplifies to O, n times m plus n squared. When tackling this problem, there are several common mistakes to watch out for. First, many assume that all words need to be compared in pairs. While this is true in a brute force approach, optimized methods, such as bit manipulation, can help eliminate unnecessary comparisons and avoid the inefficiency of O, n squared, complexity. Another common mistake is the redundant computation of common letters. For example, if you repeatedly check for shared letters between the same word pair, it wastes valuable time. Instead, by pre-computing a bit mask for each word to represent its letters, you can significantly reduce this redundancy. Edge cases are another frequent source of errors. For instance, an empty list or a single word input should return a result of 0, but failing to handle these scenarios properly can lead to incorrect outputs. Misunderstanding the requirements of the problem is also a pitfall. Some might assume that all word pairs must be considered, even when no valid pairs exist, which results in unnecessary computations. Finally, inefficient string operations, such as using set.intersection or nested loops, can slow down the solution for larger inputs. By leveraging bitwise operations, you can achieve a significant speedup and make your approach more efficient overall. Now, let's explore some insights that can help you succeed in interviews when solving this problem. A key insight is recognizing that this problem is a classic example of how bit manipulation can optimize operations when the input space is constrained, such as when dealing with only 26 lowercase letters. By representing the presence of letters in a word using bit masks, you can reduce comparisons to O, 1 time. Another useful optimization pattern is pre-computing data, like the bit masks, to avoid repetitive checks during pairwise comparisons. However, it's important to be aware of trade-offs. While the bitmask approach is highly efficient, it can be complex to implement or debug under time pressure. If you're short on time, opting for a simpler, albeit slower, solution can be a better choice. Communication is also critical in interviews. Be sure to clearly explain your approach to avoid confusion. For instance, when using bit manipulation, take the time to articulate how the bitmask represents letters and how the comparisons are performed. Finally, practicing related problems like LeetCode 338, which focuses on counting bits, or LeetCode 421, which involves optimizing pairwise comparisons using bit manipulation, can deepen your understanding of these techniques. Additionally, related problems such as LeetCode 78, which explores using bit masking to efficiently generate subsets, and LeetCode 268, which applies XOR operations to find a missing number in a sequence, can further reinforce your understanding of bit manipulation. Now let's consider alternative approaches and their trade-offs. The brute force approach is straightforward to implement but becomes inefficient for large inputs due to its n² complexity. On the other hand, the optimized bit manipulation approach offers significant efficiency with n pre-processing in n² comparisons, where each check is 1. However, it requires a strong grasp of bitwise operations. A hashing approach is another option, where hash sets can store the letters of each word. While this method avoids using bitwise logic, comparisons are slower at k per word, where k is the average length of the word. Lastly, though rarely used for this problem, a sorting and two-pointer approach can be applied after sorting words by length. However, this method is only suited for specific variations of the problem and may introduce unnecessary complexity. Choosing the right approach often depends on the constraints and trade-offs of the problem at hand. Great job! We've covered the problem maximum product of word lengths, explored a highly efficient bit masking solution, and discussed key takeaways. Keep practicing these techniques to strengthen your problem-solving skills. Don't forget to like and subscribe for more lessons. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!